Intermediate car mod explained. Suspension. Suspension geometry modifications represent the next evolution beyond basic coilovers. When you've dropped your car and realized your camber curves are completely wrong, or your bump steer is making the car undrivable, these modifications become essential. Camber arms replace factory control arms with adjustable units that allow precise camber adjustment throughout the suspension's travel. Factory arms are designed for stock ride height. Drop the car 2 inches, and your camber curves become exponentially worse. Adjustable camber arms restore proper geometry, while allowing fine-tuning for specific applications. Toe arms control rear toe settings that factory eccentric bolts can't adequately adjust. Aggressive toe settings improve turn-in response, but increase tire wear. Adjustable toe arms allow precise tuning for your specific balance between performance and tire longevity. Traction rods and tension rods control longitudinal wheel movement under acceleration and braking forces. Factory rubber bushings allow excessive movement, creating inconsistent geometry under load. Adjustable units with spherical bearings eliminate compliance while allowing geometry optimization. Roll center adjusters modify suspension pickup points to correct roll center height after lowering. Lowering a car without adjusting roll centers creates handling imbalances that can't be tuned out with spring rates or damping alone. Bushing and bearing. Bushing upgrades eliminate the compliance and flex that factory rubber bushings introduce into suspension systems. When precision handling is the goal, every bit of unwanted movement must be eliminated. Polyurethane bushings replace soft rubber units throughout the suspension system. Control arm bushings, sway bar bushings, differential bushings, and motor mounts all benefit from polyurethane upgrades. These provide dramatically improved response while maintaining some compliance for street drivability. Spherical bearings represent the ultimate in suspension precision. These eliminate all compliance, providing direct mechanical connection between suspension components. The trade-off is increased noise, vibration, and harshness, making them primarily suited for track-focused builds. Motor mounts and transmission mounts significantly affect drive-train response. Solid or polyurethane mounts eliminate the movement that causes power loss and imprecise throttle response. The engine and transmission become rigidly connected to the chassis. Differential mounts prevent the differential from moving under load, ensuring consistent suspension geometry and power delivery. Solid differential mounts are essential for high-power applications, where factory rubber mounts would tear. Chassis reinforcement addresses the fundamental weakness in most factory chassis designs: insufficient rigidity for high-performance applications. When suspension modifications exceed chassis capabilities, reinforcement becomes mandatory. Strut tower. Braces connect the top of your strut towers to prevent flex under cornering loads. Factory chassis flex allows suspension geometry changes that reduce tire contact patch and create unpredictable handling. Quality braces use triangulated designs with proper mounting points. Subframe connectors tie the front and rear subframes together, creating a more rigid platform for suspension components. This is especially critical for convertibles and older unibody designs that lack inherent rigidity. Seam welding reinforces factory spot welds with continuous welds, dramatically increasing chassis stiffness. Professional seam welding can increase chassis rigidity by 40 to 60% while adding minimal weight. Frame rail reinforcement addresses weak points in factory construction. Additional plating, internal bracing, and gussets strengthen areas that experience high loads during performance driving. Cooling. Advanced cooling systems become critical as power levels increase and track use intensifies. These systems go beyond basic radiator upgrades to comprehensive thermal management. Oil cooling systems maintain optimal oil temperatures under extreme conditions. Engine oil coolers prevent oil breakdown that leads to bearing damage and power loss. Transmission coolers protect automatic transmissions from heat-related failures during performance driving. Differential coolers become necessary for limited slip differentials under track use. LSD clutches generate significant heat that can cause fluid breakdown and component failure without adequate cooling. Electric fan conversions eliminate the parasitic drag of mechanical fans while providing better cooling control. Electric fans can be programmed to operate based on temperature, vehicle speed, and air conditioning demands, freeing up 10 to 15 horsepower. Intercooler upgrades for forced induction applications dramatically improve power consistency. Larger cores, improved fin design, and better airflow management maintain lower intake temperatures under sustained boost conditions. Coolant reroute kits optimize coolant flow patterns in engines with poor factory routing. These modifications ensure even temperature distribution and eliminate hotspots that can cause detonation. Exhaust system modifications at the intermediate level focus on optimizing flow characteristics and scavenging effects. This goes far beyond basic catback systems to complete exhaust engineering. Headers replace restrictive factory exhaust manifolds with tuned-length primary tubes that optimize exhaust scavenging. Equal-length designs ensure consistent exhaust pulses, while unequal-length headers can provide torque benefits in specific RPM ranges. Primary tube length and diameter must match engine characteristics. Longer primaries favor low-end torque, while shorter tubes optimize high RPM power. Diameter affects velocity. Too large hurts scavenging, too small creates restriction. Collector design significantly impacts performance. Merge collectors gradually combine exhaust streams, while step collectors create specific pressure waves. Anti-reversion chambers prevent exhaust backflow during valve overlap. High-flow catalytic converters maintain emissions compliance while reducing restriction. Modern metallic substrates flow significantly better than ceramic units while providing faster light-off times and better durability. Exhaust system tuning includes resonance control and thermal management. Proper tube sizing, resonator placement, and heat shielding optimize both performance and sound characteristics. Intake system modifications optimize airflow delivery to maximize volumetric efficiency. These modifications go beyond basic cold air intakes to comprehensive airflow engineering. Intake manifold upgrades improve airflow distribution and velocity characteristics. Larger plenums reduce restriction, while velocity stacks optimize airflow into individual runners. Runner length tuning creates resonance effects that improve cylinder filling. Throttle body upgrades increase airflow capacity for modified engines. Larger diameter bodies reduce restriction, but proper sizing is critical. Oversized units can hurt throttle response and idle quality. Individual throttle bodies provide ultimate throttle response by eliminating plenum volume. Each cylinder receives its own throttle plate, creating immediate throttle response and distinctive intake sound. Intake port modifications optimize airflow into combustion chambers. Port matching ensures smooth transitions between components, while port shaping and polishing can improve flow characteristics significantly. Variable intake systems adjust runner length or plenum volume based on RPM. These systems optimize torque curves by providing different intake characteristics for different engine speeds. Tires. Wheel and tire technology at the intermediate level focuses on maximizing grip through proper compound selection, sizing, and setup optimization. Our compound track tires provide maximum grip through specialized rubber compounds and construction. These tires generate 20 to 30% more grip than street tires, but require proper heat cycling and have limited tread life. Wheel offset optimization affects handling characteristics by changing scrub radius and suspension geometry. Proper offset selection can improve turn-in response, reduce understeer, and optimize tire contact patch shape. Tire pressure optimization becomes critical with performance tires. Proper pressures maximize contact patch while preventing overheating. Tire pyrometer readings help determine optimal pressure settings for specific applications. Wheel width selection affects tire sidewall support and contact patch shape. Wider wheels reduce sidewall flex, but must be properly matched to tire width to avoid creating a narrower contact patch. Tire compound selection varies based on application. Autocross compounds prioritize grip over longevity, while endurance racing compounds balance grip with wear characteristics. Drivetrain. Advanced drivetrain modifications optimize power transfer while reducing parasitic losses. These components handle increased power while improving response characteristics. Lightweight flywheels reduce rotational inertia, improving engine response and acceleration. Single-mass flywheels eliminate dual-mass complexity while reducing weight by 15 to 25 pounds. The trade-off is increased noise and vibration transmission. Close ratio gear sets keep the engine in its power band more effectively during spirited driving. These modify the spacing between gears to reduce the RPM drop during shifts, maintaining optimal power delivery. Limited slip differential upgrades improve traction and handling characteristics. Mechanical LSDs provide consistent operation, while electronic units offer variable characteristics. Proper differential selection depends on intended use and power levels. Driveshaft upgrades reduce weight while handling increased power. Carbon fiber units reduce rotational mass by 50 to 70%, while providing excellent strength characteristics. Aluminum driveshafts offer good weight savings at lower cost. CV joint upgrades handle increased power and suspension modifications. Racing CV joints provide strength for high-power applications while maintaining smooth operation through extreme angles. Engine management. Engine management modifications bridge the gap between basic tuning and standalone systems. These modifications provide enhanced control while maintaining factory integration. Piggyback ECU systems intercept and modify factory ECU signals to provide additional tuning capability. These systems allow boost control, fuel enrichment, and timing adjustment while maintaining factory diagnostics and emissions compliance. Wideband oxygen sensors provide accurate air-fuel ratio monitoring for proper tuning. Factory narrowband sensors only indicate rich or lean conditions, while wideband sensors provide precise mixture ratios across the entire operating range. Fuel rail upgrades improve fuel distribution and flow capacity for high-power applications. Larger diameter rails reduce pressure drops while providing better fuel distribution to individual cylinders. Fuel pressure regulators provide precise fuel pressure control for modified engines. Adjustable regulators allow fine-tuning, while rising rate units increase pressure with boost for forced induction applications. Catch cans prevent oil vapor from entering the intake system, reducing carbon buildup and maintaining consistent air-fuel ratios. These are especially important for direct injection engines and forced induction applications. Boost controllers provide precise turbo boost management beyond factory capabilities. Electronic controllers offer multiple boost maps, progressive boost control, and safety features like overboost protection. Electrical system. Electrical system upgrades become necessary as performance modifications increase electrical demands. Modern performance cars require significantly more electrical capacity than factory systems provide. High-output alternators provide additional charging capacity for performance accessories, lighting systems, and electronic engine management. These units typically provide 50 to 100% more output than factory alternators while reducing parasitic drag. Battery relocations serve dual purposes, improving weight distribution and providing safety benefits. Moving the battery to the trunk or rear seat area can improve front-to-rear weight balance while protecting the battery from engine heat. Motorsport-grade wiring harnesses provide better reliability and performance than factory wiring. These use higher quality materials, better connections, and improved routing for performance applications. Grounding kits improve electrical connections throughout the vehicle. Better grounds reduce electrical resistance, improving performance of ignition systems, fuel injectors, and electronic components. Performance ignition coils provide stronger spark energy for modified engines. Coil-on-plug conversions and high-energy ignition systems support increased power and boost levels. Performance monitoring. Performance accessories optimize various systems while providing monitoring capabilities essential for high-performance applications. Underdrive pulleys reduce parasitic drag from accessories, freeing up horsepower for performance. These slow down alternator, power steering, and air conditioning compressor speeds to reduce engine load by 10 to 15 horsepower. Data acquisition systems provide essential monitoring for performance driving. Basic systems record lap times and basic engine parameters, while advanced units monitor suspension loads, brake temperatures, and driver inputs. Tow hooks provide essential recovery points for track use. Front and rear hooks allow safe vehicle recovery without damage to bodywork or suspension components. These are mandatory safety equipment for most track events. Temperature monitoring systems track critical component temperatures during performance driving. Oil temperature, coolant temperature, and intake air temperature monitoring prevent damage from overheating conditions. Harness bars provide proper mounting points for 4-point and 6-point racing harnesses. Proper installation requires understanding load paths and mounting requirements to ensure safety effectiveness. These modifications represent the true middle ground between basic bolt-ons and expert-level builds, focusing on performance optimization, handling, and system integration. Each modification requires understanding of engineering principles and often professional installation. The key is systematic development, addressing weaknesses in order of priority while maintaining overall vehicle balance. These modifications separate casual enthusiasts from serious builders, requiring greater investment in knowledge and execution, while delivering transformational performance improvements. If you enjoyed this video, subscribe for more breakdowns. See you in the next video.